Okay, so do I have anybody that is feeling confident about the differential equation that they created for this problem? If not, I will pick somebody at random. All right, random picker it is. Jesse, do you have a differential equation for this problem?
Yeah.
Okay, so what's the differential equation that you came up with?
dn over dt equals k times n of t.
Is equal to k times n times the number of unit and the time t. Times t, like this, or times n of t?
I did n of t.
Okay, so in this case, it's n times t because it's proportional to both the number of units and the time t, right? So this is like saying, I'm implicitly writing this as k times n of t times the actual time, right? So it's proportional to both things, both the number and the amount of time. Does that make sense?
Okay, yeah.
Yeah, all right. Show of hands for those of you who had come up with the exact same differential equation. Whoops. That's not what I wanted to do. Oh my God. Okay, whatever. All right. So this is the first thing that we have, which is the differential equation. Then we need some initial conditions. Does anybody have an initial condition that they would like to share? And if not,
Sure.
yeah, okay, Jesse?
N of 0 equals 400.
N of 0 is equal to 400, and?
N of 2 is 1200.
And N of 2 is equal to 1200. Show of hands for those of you who had the same thing. Okay, can I see a show of hands for those of you who might have some questions about this? Because I see that not that many people got exactly the same differential equation, and I'm worried that maybe somebody does not understand what's going on.
I wanted to ask,
yeah.
What's the K for?
The K is just the constant of proportionality. So all that we know over here is that the metal company has a production that increases at a rate proportional to these two things, which means it might be 1 times n times t, but it might be 2 times n times t, it might be 7 times n times t, and we don't know what the constant of proportionality is going to be. So that means that when we say proportional to, that's going to mean some number times n times t, which is a constant, but we don't know what the value of that constant is going to be. Okay. Okay, so in that case, we're going to start by solving the differential equation, and then we're going to see if we can use our initial conditions in order to actually find what the specific value is at 4. Okay, so here we go. We have the differential equation is dn over dt is equal to k times n times t. So I'm going to write it down over here. dn over dt is equal to k times n times t. And I'm trying to solve this as a function n in terms of t, right? And now the only technique that we have so far is to say, okay, well, I have two variables, n and t. I want to try to integrate with respect to each of them. And so what I'm going to try to do is separate the whole equation that I have so that in one side of the equation, I have everything in terms of n, and on the other side of the equation, I have everything in terms of t. In that way, I'll be able to integrate left-hand side independently from right-hand side, and then hopefully I'll find an expression for n. Right, so in this case, for example, I'm going to divide both sides by n, which means that I get on the left-hand side 1 over n dn. And if I also multiply by dt, I'm going to get on the right-hand side k times n, times t times dt. Show of hands if you understand this step. Okay, that's good. So this is the next step, which is to actually separate the variables, and then we are going to have to integrate each of the sides separately. So on the left-hand side, I'm going to have that the antiderivative of 1 over n is going to be ln of absolute value of n. Whereas on the right-hand side, the antiderivative of k times t dt is going to be equal to k times the antiderivative of t, which is t squared over 2, plus a constant of integration. What we said last time is we can just put the constant of integration on the right-hand side, because putting it on the left and on the right-hand side will always lead to me combining them anyway, and so there's no point in wanting to separate it, like identify each one of them. Okay, so now we have ln of absolute value of n is equal to k times t squared plus c, which means that if I want to solve for n, I'm going to have to get rid of the logarithm that I have on the left-hand side. And one thing that I tried to emphasize at least last time was that if I want to get rid of a logarithm, I have to put that on the exponent of an exponential. So that means e to the ln of n is equal to e to the power of k times t squared over 2 plus c. On the left-hand side, e to the power of ln of n is just going to give me n. Whereas on the right-hand side, I'm going to have e to the k times t squared over 2 times e to the power of c, right? Because e to the power of something plus something is going to be equal to e to the power of the first thing times e to the power of the second thing. Show of hands, those of you who understand. All right, and then because this is e to the power of c, and the constant here can be arbitrary, I'm going to write this as a new constant, which is called d, and I get a final expression for the production in terms of time, which is n is equal to some constant d times e to the power of k times t squared over 2. Right, and so this is going to be my general solution of the differential equation that I have over here. Any questions? Okay, now this is the general solution of the differential equation, but I want the particular solution that satisfies the condition n of 0 is equal to 400 and n of 2 is equal to 1200. Now, before we had talked about the fact that we always need one initial condition, and in this case we seem to have two initial conditions. The reason that we have those two initial conditions is that we also need to solve for one other term in our expression, which is the constant of proportionality. So if that constant of proportionality were given to us, we would only need one initial condition, but in this case, we're actually going to have to figure out two things for our function. We're going to have to figure out the value of the constant d, and we're going to have to figure out the value of the constant k. Right, so this is why we have two conditions in this case. So what I'm going to do is start with the condition n of 0, which is usually the easiest one to evaluate because 0 has nice values that come out of it. And then I'll use whatever value I find for one of my constants when I'm trying to solve for n of 2. So that means, oops, I have gone. What am I doing? Oh yeah, so n of 0 is equal to 400, right? So 400 is the value of the production when, like, at the present time. So after 0 years, the production is equal to 400. But also I know that the production is given by a function of this form, right? So I'm going to plug 0 into that expression, and I get d times e to the power of k times 0 squared divided by 2, which means that n of 0 is equal to d times 0, e to the power of 0. And this is equal to d, right? Now remember, at this point, I haven't done anything. I've just plugged this into the expression that I already know gives me the production for each of the years. And I found that at the year 0, the production is going to be equal to d. Now what I'm trying to do is find the value of d, and I'm lucky enough that I was told that after 0 years, the production was equal to 400. So this means that I can set this to be equal to 400. I can force it to be equal to 400, and that leads to the conclusion that d has to be equal to 400. Okay, and so from this point, I have now obtained that n of t, or n at any other given time, is going to be of the form 400 times e to the power of k t squared over 2. Do I have any questions about this? Okay, so at this point, what I've done is to find the value of d, and then I can replace that value into the expression that I know for the production at any given year, but I still have to find the value of k. Right? So in order to find the production, in order to find the value of the constant k, I'm going to do the same thing, but for n is equal to 2. So I have that n of 2 is equal to 1200, but also n of 2 is equal to 400 times e to the power of k times 2 squared over 2. Show of hands if you understand that step. Okay, still had about 4 hands that did not go up. If they didn't go up because you actually didn't understand something, please unmute your microphone and let me know. So this means that this is 400 e to the power of 2 squared over 2 is equal to 2, so 2 times k. And now I know that 400 times e to the 2k is the production after 2 years, but that also has to be equal to 1200 because that's the value that I was given for the production after 2 years. Right? So at this point, I'm going to have that e to the 2k, if I divide both sides by 400, is going to be equal to 300. And now I need to solve for k over here. Now when I'm solving for k, I have to be careful because I have k on the exponent of e, and so I need to find a way to solve for that exponent that I have over here. So in the same way that I said, okay.
Wait, miss.
Yeah.
How is it 300?
Because it's 1200 over, it's 3,
Yeah,
sorry.
3.
I don't know how to divide. Thank you. Ah. Okay, one day I'll get this. There you go. Thank you. So I have e to the 2k is equal to 3, which means that if I try to solve for 2k over here, I'm going to do the opposite of what I did here, right? So I said, if I want to get rid of a logarithm, I have to put it on the exponent of e. Well, here, if I want to get the exponent of e, I need to apply a logarithm on both sides, right? So I'm going to have that ln of e to the 2k is equal to ln of 3, which means that 2k is equal to ln of 3 like this. And that tells me that k is equal to ln of 3 over 2. Who understands this? Show of hands. Okay, so you guys are understanding everything. Now you just have to actually do your homework to realize that you can do it on your own. As finish the problem, I'm being asked what the production is in 4 years, which means that I'm looking for n of 4. So the first thing I'm going to do is to simplify the expression for just n. So n is equal to 400 times e to the power of k, which is ln of 3 over 2, times t squared over 2. Right, so all that I'm doing here is replacing the value of k into the expression that I already had for n. Now, before I actually get to evaluate this, I'm going to simplify this because I have e to the power of ln of something, which means that there's probably something that I will be able to simplify here. And in general, I'm going to suggest that you try to do this because if you simplify before, then you don't have to round as you go in evaluating this function. And instead, you can actually just evaluate everything at the same time. You're going to see what I mean by this. Once we simplify the expression, you're going to see it's a lot easier than it looks like. So here I'll have that this is the same as 400 times e to the power of ln of 3 times t squared to the power of, divided by 4, right? And the reason that I'm doing this over here, I'm combining the denominators. What I always want to do is to separate the thing that is inside the logarithm from the thing that is not inside the logarithm, so that then I can see what I need to cancel out with the exponential. So you guys probably all remember, I'm assuming that you all remember, that e to the power of a times b is equal to e to the power of a, the whole thing to the power of b. If you don't remember, now you remember. This is something that you need to know. So that means that when I'm trying to evaluate this over here, to simplify it, I'm going to get 400 times e to the power of ln of 3 to the power of t squared over 4. Which means that now I can simplify e to the ln of 3, right? So the whole point of my doing these two steps is to have just one piece that is e to the power of ln of something so that I can simplify the exponential and the logarithm, and then I have an easier term to evaluate the power for. So that means I have 400 times e to the power of ln of 3 is just 3 to the power of t squared over 4. Do I have any questions about this, or does that make sense?
Yeah.
Yeah.
So
Question? Yeah.
how come it just becomes 3?
Same thing as here. We have e to the power of ln of n is equal to n. Well, here
Okay.
e to the power of ln of 3 becomes 3, right? So we have always that. I'll put that one in red here as well. When I have e to the power of ln of something, the result is always going to be the something.
Okay.
Okay, so that's exactly what I did here, which is why I need to separate this into something that has a logarithm versus everything else that is not included in the logarithm, so that I can see exactly what this is. So now this is my final expression for n in its simplified form, which means that now if I want to evaluate n at 4, it's going to be a lot easier. I'll have n of 4 is going to be equal to 400 times 3 to the power of 16 over 4, which is equal to 400 times 3 to the power of 16 over 4 is 3, so times 3 to the power of 4. 3 to the power of 4 is 3 times 3, which is 9, times 9 again, so that's 81. This is 400 times 81, which is equal to 32,400. And that means that after 4 years, the production will be 32,400 units. Show of hands if you understood everything. Okay. Do I have any questions or anybody that doesn't understand either of the steps, which is completely fine. If you don't understand something, chances are somebody else is being a little bit more shy than you and also doesn't understand one of the parts of the problem.
Miss?
Yeah.
So how come E exponent 2k equal 3?
Okay, so that comes from here, right? So I have 400 times e to the 2k is equal to 1200, and so if I divide both sides by 400, I get 3.
Okay.
And not 300, like some people would say. All right, Shine, your hand is still up. Okay, do you have a question? Shine lights. Can you please raise your hand if you have finished copying what I have on the board? All right. So I'll put another example on the board. You also have to solve this in the same exact way. So you have to find the differential equation, then the initial condition, and then try to solve for the things that you don't know in order to evaluate the final result. Here we go. We have that. The rate of increase, let me just check something. Okay, no, so here we go. We're gonna do one that's a little bit more difficult, and then I'll leave you some time to work on problems. It seems like you need to be supervised while doing problems. So we have that a rumor starts spreading at a rate that is proportional to two things. That is proportional to the number of people that have heard it, which is denoted by n, and the number of people that have not heard it. And this is in a population of 100,000 people. Okay. Initially, 10 people had heard the rumor, And after 3 weeks, 200 people had heard the rumor. How many people will have heard it after 10 weeks? Okay, so you can start by writing down the differential equation that corresponds to this and the initial conditions. You have 2 minutes to do this. And if you can start trying to think about how to actually solve this problem through integration. So here we have already set up the equation. We have set up the integrals that we want to evaluate. We know the right-hand side is easy to evaluate, but now we want to evaluate the integral on the left-hand side. What I have here is the integral of 1 over n times 100,000 minus n. Is there a technique that allows you to integrate for that? Oh, I have someone in the chat. So I have 1 over 100,000 times n minus 1 over n squared. Let me just write that down. So I'll have here, this would be the integral of 1 over, and I'm guessing what happened there is we multiplied the n over. So we got 100,000 times n minus n squared with respect to n. And from here, what you propose is that we have integral of 1 over 100,000 n minus 1 over n squared. Does this work, everyone? Show of hands for those of you who agree with this idea.
No.
Show of hands for those of you who disagree with this idea. Why should this work or not work? I heard a no. Why does this not work?
Like you have a number divided by a plus b, you cannot split them.
Exactly. If you have a number divided by a plus b, this is not the same as that number divided by a plus the number divided by b. Right? This does not work in this case. So this is not going to be the right solution. Oops. But it brings up an interesting idea, which is the fact that these two expressions would be easier to evaluate, right? So there are some rational expressions that we can evaluate and some that are a little bit more difficult to evaluate. Now, how can I simplify this in a way that I can actually integrate?
You factor it by n.
Okay, so the factor is already here. So this is already the expression by n. And then
no,
what do I
mean by n squared?
Even if I factor by n squared, then I'll have a fraction within a fraction because this will become 100,000 over n.
No, I mean like n squared times bracket 1 minus 100,000 divided by n. Yeah, and bracket.
Divided by n.
Yeah.
Yeah, so that would be the denominator, and then I have something like this, which means then I could evaluate this, but this is a complicated expression to have at the denominator, so this is really not going to help me that much.
Or you can set it as view.
Actually, that's probably not a bad idea. Let me see. Oh, that's a good idea. Let's try it. Does that work? Does that work? Yeah, that should work. So, is that going to be the case? Is equal to that. And then, well, that's not the technique that I had in mind, but I don't see why it shouldn't work. Yeah, that should work. That's a good idea, yeah. So we're going to do that, but what I was thinking was more partial fractions. Does everybody see why partial fractions could work in this case? Maybe, maybe not. Can I see a show of hands of those of you who understand why partial fractions would work? It's really not enough hands. So what we have over here, I'm going to solve this in the way that Chris proposed, but partial fractions would also work in this case if you set this to be equal to a over n plus b over 100,000 minus n, and then you solve for a and b, right? Because then you would multiply the denominators and you would get an expression like this. But Chris's way should work, and so I'm going to do it with that one. Might even be easier than partial fractions. Let's try that. We're going to have that the integral that we are evaluating is the integral of 1 over n times 100,000 minus n, which means we're going to factor another n over here, to get that this is the same as the integral of 1 over n squared times 100,000 over n minus 1. Minus 1. Now, this is not an obvious idea. This is not a problem that either in the partial fractions way or in this substitution way. This is not something I would expect you to do just, through your own inspiration during an exam or something like that. But it's something that I want you to go over when you're trying to solve problems, just so that you see what we can do with differential equations. So over here, what Chris proposed is that we use the denominator as a substitution, and we do a u substitution. And the reason that we are going to be able to do this is that then we'll have 1 over n squared, which is going to help me find and replace the derivative of 100,000 over n. Right, so I'm going to rewrite this in a way that the substitution becomes a bit more clear, which is 1 over 100,000 over n minus 1 times 1 over n squared dn. Right? And the main lesson that I want you to remember about this is that you have all of the techniques that you have found in integration. They are all, you can use all of them in order to solve this type of problem. So this is going to be our u. And hopefully this will help us find our du. Okay, so we'll have the following. U is equal to 100,000 over n minus 1, which means that du is going to be equal to the derivative of 100,000 over n, which is minus 100,000 over n squared with respect to n. And so that means that if I want to replace just 1 over n squared dn, I'm going to get that this is the same as du over minus 100,000. This is going to be equal to 1 over n squared dn. Show of hands for those of you who understand what's going on the board. Okay, the hands are not raising that fast. I see Ashley, Costa, Jesse, Juliette, Michael, Sabrina. I didn't see your hands up. Is there any reason why the hands are not up? Is there any part that is not clear?
There's just a lot going on.
And there is a lot going on. Okay, so I'll just go over it from the beginning. That's good?
Yeah.
All right, so I started with this expression over here, right?
Yeah.
And then what we did is we factored out an extra n from here. So we're taking an n out, which means like we're dividing everything inside the bracket by n, and then we're multiplying it outside of the bracket, right? So that's what I do when I factor. I divide everything inside the bracket by a number, and I multiply it outside. So that's what's happening here. Is that good?
Yes. Thank you.
All right, now I have 1 over n squared, and I have 100 over n minus 1. And what I did is just separating those two terms. And what that allows us to do is that we have 1 over n squared dn over here, which seems to be very similar to the derivative of the new denominator that I have over here. What that makes it, what that does is it makes it easier for us to do this integration, right? Because then we know that we can do the substitution using this denominator. And if we use this denominator, we'll be able to use the 1 over n squared dn in order to replace the derivative of the new variable u that I have. And so over here, all that I'm doing is to actually formalize that substitution.
Mm-hmm.
Does that make sense?
Yeah.
All right, so then we're going to replace each of those pieces. We're going to have integral of 1 over 100,000 over n minus 1. So this is just 1 over u. And then we said 1 over n squared dn can be replaced by du over minus 100,000. if I integrate this, I'm going to get that this is minus 100,000 times ln of absolute, oops, minus 1 over 100,000. Minus 1 over 100,000 times ln of absolute value of u, which is the same as saying minus ln of, and then I can back substitute, which is 100,000 over n minus 1 divided by 100,000. All right, is this okay for everybody? Yeah, so this is my u, this is my u, and then I replace that with the actual expression that the u is replaced. Do I have any questions about this, or is that okay for everyone? Now keep in mind that this is a difficult problem, okay? This is not a standard exam problem or anything like that, but it is an example that I want to cover because this is one of the classical examples that we had talked about. All right, so if this is the case, I'm going to write that as a result of the left-hand side, and then the right-hand side is really easy for that. Right? So the left-hand side over here gives minus ln of 100,000 over n minus 1 divided by 100,000. And on the right-hand side, if I integrate k times dt, I just have k times t plus c. Do I have any questions about this? Show of hands for those of you who understand everything from here, that at least follow all the steps, even if maybe you think, oh, I wouldn't have had this idea, but you follow all the steps that I did. Okay, all right. So I think everyone pretty much answered yes, and if not, then please do interrupt me. Now I'm just going to finish solving this type of problem by trying to solve for n now. Matthew, your hand is up. Is that because you have a question or because you forgot to lower it? Okay. So what I have now is an expression, but I want to solve for n over here, which is the denominator. Right? So ideally, I'll be able to solve everything. So put everything, all the operations on the right-hand side, and then solve for the value of n that I have here. Okay, so I'll do the first couple of steps of that by first multiplying by negative 100,000, right? So why negative? Because I want to get rid of this one, minus, and by 100,000 because I want to get rid of this denominator. So that means I have ln of 100,000 over n minus 1 is equal to negative 100,000 times k times t plus negative 100,000 times c, so minus 100,000 times c. Show of hand if you understand the transition from this step to that step.
How come it's minus 100,000 times c and not just kt plus c, like in brackets?
It's the same thing. It's just that I've already distributed the minus 100,000.
Okay.
Okay, so it's the same as minus 100,000 times kt plus c, or distributing it right away. Okay, so at this point, I'm going to take the exponential on both sides. Yeah, if I take the exponential on both sides, on the left-hand side, I get e to the ln of 100,000 over n minus 1. And on the right-hand side, I get e to the power of minus 100,000 times kt minus 100,000 times c. I'm going to erase now the whole right part over here. So this over here, I'm going to erase unless there's somebody else that's still copying the right-hand part of the board. Okay, and now I know that if I simplify on the left-hand side, I have 100,000 over n minus 1 is equal to e to the minus 100,000 times k times t times e to the minus 100,000 times c. And because c is an arbitrary constant, so it can take, we can take any value that we want, we actually have that this term over here can be replaced by some other arbitrary constant, which I'm going to call in this case, as very often is the case, d. Right, which brings me to the following expression, which is that 100,000 over n minus 1 is equal to d e to the minus 100,000 k t. And then I'm going to solve for n by just adding 1 and then putting this on the denominator. So I have 100 over n is equal to, and I can add 1 on both sides, so 1 plus d e to the minus 100,000 times k times t. And then if I multiply both sides by n and divide both sides by 1 plus d times e to the blah, 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 then I'm going to have that 100. If I multiply by n, that's going to simplify this n, and I'm going to get that on the right-hand side alone. And if I divide by 1 plus d e to the minus 100, I'm going to get that on the denominator. E to the minus 100,000 times k times t. Is this okay for everybody? Can I see a show of hands for those of you who understand this? Steps, following the steps. Okay. All right, good. All right, so we've done a lot of work, and here still, the only thing that we have solved is the original differential equation. Again, I will repeat, this is a difficult problem. This is the only problem of this level that you'll look at. I think you have one of them in the homework, but that's it. I wouldn't expect you to go through this problem unguided during an exam or a quiz. All right, so we have now solved the initial differential equation. What we're going to try to do now is to find the values that we don't know yet in our expression based on the initial conditions that were given, right? So we know that we still have to evaluate the value of k over here, and that we still have to evaluate the number d that I have over here. All right, according to you, how will we find these values?
Using the initial condition?
Using the initial conditions. So I'm going to start with n of 0, and I'm going to see if I can solve for one of them. And then I'll have n of 3, and I'll try to solve for the other one. And so I have here. I'm going to start by, there you go. Okay, so at this point, we already know what my expression is going to look like, which is this one over here. I'm going to try to use the initial conditions in order to find the values of D and K. So we're going to have the following. First, n of 0 is equal to 10, which means that n of 0, which is equal to 100,000 divided by 1 plus d times e to the 0 is equal to 10. Right? So what that tells me is that 100,000 divided by 1 plus d is equal to 10. And now I have to solve for d. So I'll have 1 plus d on this side is equal to 100,000 divided by 10, which is 10,000. With the final conclusion that d is equal to 9,999. Right, so what I did here is I multiplied by 1 plus d, and I divided the left-hand side by 10. So 100,000 divided by 10 is 10,000, and on this side I just get 1 plus d, and then I just have to subtract 1 from both sides. Do I have any questions? Don't worry, you'll have today's class plus probably Tuesday's class in order to practice problems like these. All right, so from here we get that n is given by the following type of expression, which is 100,000 divided by 1 plus 9,999 times e to the minus 100,000 times k times t. And then n over here, we know that when t is equal to 3, this is going to be equal to 200. Right? So the idea over here is that now we're going to find the value of k. So n of 3 is equal to 200, but n of 3 is also equal to 100,000 divided by 1 plus 9,999 e to the minus 100,000 times k times 3, which is the same as 100,000 over 1 plus 9,999 times e to the minus 300,000 k. Do I have any questions about this, or is that all right? All right, so then the next step over here would be equal to, so we would have to make 200 equal to this expression and then solve for k. All right, do I have a show of hands for those of you who understand what I'm saying here? Okay, so here's what we're going to do, because I don't want you to get lost on what we're doing here. I'm going to ask you to finish this problem at home, mainly because I think I want you to go over the explanation again, and I want you to see, exactly how we found each of the steps. And so for homework, you're going to finish this problem, which means two things. First, it means you're going to find the value of k. You're going to solve for k, which I think is important that you know how to do by doing some algebraic manipulation. So you're going to have to solve for that value of k based on this equation. And then you're going to have to find the value of n after 10 weeks. Is that clear for everybody? Yeah. Do I have any questions about the steps that you need to follow? Okay, so I'll leave that as homework, and maybe I think a better use of our time right now will be to actually practice some easier problems, so that you have a couple of examples before going on the long weekend. So what I want to ask you to do is to go to problem set number 10 and to start working on problem number 6, which is to use the problems that were modeled in problem number 1 and to actually solve them using differential equations. Does everybody understand this? Show of hands. Okay, so go to problem number 10 and work on problem set number 10 and work on problem number 6. I think that's a better use of your time. During the weekend, that's what I want you to start to do. So all the problems 1 through 6. Put a note on problem number 6G because it's just another version of this problem over here. Okay, so this is the same as problem number 6G. So what you can do is try to solve this problem completely at the end to verify if you understand how this was done by modeling exactly what I did. But really, the main thing is for you to be able to solve problems 1 through 6, not necessarily G, without looking at the solution. Does everybody understand that? Yeah, okay, so, yeah, there's a question, Juliette?
No, I was just agreeing.
Yeah, just saying, okay. So then you can work on this now, and if you have any questions, you can raise your hand. I think it's really important that you get some practice, and I think maybe this was a problem that was a little bit too difficult to address today. So do some practice. You'll still have some practice on Tuesday, all right? That's it. Get to work.